haven't even done anything yet and I'm getting applause. This is a great start to the day. Did you turn that one off? Yeah, good. Okay, so there's this rate session thing. Like Jonathan says, please rate at the end of the talk and ask me questions there. And I'm going to hopefully have about 10 minutes at the end for questions, but we all know how that goes, right? So I'm going to talk to you about C++. It's the oldest new language. This is sort of rather pejoratively called the old school languages, but I would like to sort of try and leave you with the impression that C++ is not a fuddy old language. It is, in fact, a cutting-edge, awesome language that you should all be using. So who uses C++? First of all, of you lot. One person uses C++. Anyone else using C++ currently? 2, 3, yeah, some people? Wow, okay. This is useful because it tells me whether or not I should go more into the details of some of the warty bits of C++, or whether I should concentrate on the bits that are interesting to me about choosing C++ as a language. So in answer to who uses C++ more generally, like industry side of things, and I'm sorry, people are waving me from outside, I've used C++ pretty much exclusively through my career. And I've spent 10 years in the games industry, and in the games industry, C++ is a pretty good choice for writing engines and 3D systems. Back at the very, very beginning, like the late 90s of my career, it was still C rather than C++, but C++ became pretty much the standard after that. Obviously, scripting within games is done in other languages sometimes, Lua and other bits and pieces, but C++ is a good place to start. I've worked in finance, and finance, certainly if you're doing anything that has like a high throughput or a low latency flavor to it, C++ can be a good choice there too. Embedded devices, again, C is also a good choice for these things, but C++ is becoming more and more of a good choice because it gives you the flexibility of a high-level language and all the constructs that come with that, but still be able to get down and poke hardware registers as you might need to be able to do. And I've played around on cell phones writing MPEG decoders and things like that, and C++ was a great choice for that kind of thing and talking to like hardware MPEG devices. And then servers, if you type a web query right now, it's almost certainly going to be handled by something written in C++ on the back end. But why would you pick C++? So obviously, the first thing that springs to mind for most people about C++ is that it's something you write in if you want high-performance code. And I'm going to make no apologies. This is an evangelical talk about C++. Other languages are available, and in fact, I will make reference to them, but I'm not an expert in other languages, so I will try and keep my mentions of other languages to factual and not sort of emotional, because I'm certain there are people in this audience who know a lot more about those languages than I. So I'm going to surprise you. The things about C++ that I think make it a good choice are these: value types, clear object lifetimes, and then third, performance. So performance obviously is a very important thing for a lot of the applications I've just described, but there are aspects of C++ that make it a really good choice even if you don't need to be writing super performant code. I'm going to come back to these in a few slides and explain a little bit more about what I mean by a value type and what the clear object lifetimes mean. But by now, somebody in this audience, possibly all of you, are thinking, but isn't C++ that horrible thing with the multiple pages of error messages and all the crashes and the memory leaks and all the security flaws and all that stuff? And of course, yes, to some extent, it was. That's old C++. New C++ is better. And of course, because it's backwards compatible, you can still write old style C++ and leave yourself open to all these problems, but I'm going to hopefully explain to you that you shouldn't be doing that anymore and that there is a better choice for you. So what has changed in the language? I'm going to give you a little table here and give you the highlights of each revision of the language. Many of you may not know that C++ has been updated fairly frequently. Well, I guess we started in 1998 with like the first real version of C++ that was a standard. And the highlights of that were memory leaks, use after free, crashes, all those things. Now, obviously, those are not really highlights, but I want to try and make a point here. And then in 2011, a new standard for C++ was released. There was a committee meeting in the late 2000s, and for those of you who who know about these things, it was called C++ OX for forever because they thought they were actually going to get it out in the 2000s, but it sort of overran and eventually became C++ 11. So there you go. But we got a whole raft of awesome new features. The first thing is this keyword auto. Now, if you're as old as me, you may know that auto has always been a keyword in C, and it's like the opposite of static, and it's also the default, so you would never write int I as a, so you'd never write auto int I, semicolon, to like define a variable called I, but that's what it means. The auto means it's automatic storage, it means it's on the stack, but nobody used that, so they co-opted the keyword, and auto now means you guess the type, compiler. So if I do auto I equals 0, semicolon, I's type will be derived to be an integer. And if I do auto I equals false, then I will be Boolean, or if I call some complicated function, it will be whatever that complicated function returns. And that's super handy. You've probably, if you're like used to programming in less strongly typed languages, you're used to things like let, or other sort of ways to just say, I just need a variable called x, and it's this thing over here. C++ is not weakly typed, so there is a strong type associated with that, but the auto says, you work it out, compiler, you figure it out for me, and it gets rid of so much of the boilerplate code that you would otherwise need. I've got some examples of that coming up. We got range for. So before this, if you wanted to iterate over a container or a sequence of things, you'd either have to count from 0 to the number of things in the container, or you'd have to use these complicated iterator trait type things where it's like vector of int colon colon const iterator. And that's already a huge amount to type out, and you start at the beginning and you'd keep iterating until you hit the end. And that's just very inconvenient. So we get range for. So now I can go over a container by going for auto I colon container, and I will get for every element in that container, I get a variable called I, and I didn't even have to know what type it was because the auto thing has worked that out for me too. We get lambdas. So I can now define a small function in line where I need it, and those lambdas can capture variables by either copy or reference from their enclosing scope. And that's a really powerful thing if you're writing functional style programming, where you might have an algorithm that says, I need to combine a bunch of things together, and I'd like to supply the combining function. Now, previously, you'd have to like define somewhere else a function that is the how to combine things function, and you'd have to refer to it in the program at the point where you were calling it. But now you can actually just define in that spot the function itself. And even more importantly, you can capture some like local variables or state, basically a closure. We got move, which I've just put down as move here, but there's a whole bunch of machinery that was added to the language to support the idea that object lifetimes can be transferred. So, object ownership can be transferred. So I can clearly define when I'm giving an object to somebody else and I don't need it anymore. And that's really important with the next point, which is smart pointers. I can write, and if the standard now provides a set of template objects which look like pointers, but under the hood, they actively manage the thing that they're pointing at. So whereas before you might just do int star I equals new int, and then just remember to delete I when you've finished with it, else you've got a memory leak, I can now make a unique pointer to I, and a unique pointer says, I uniquely own the thing that I'm pointing at, and when that unique pointer falls away out of scope and can't be reached anymore by the compiler, its destructor will run, and its destructor will clean up the piece of memory that it's pointing at. And that's extremely powerful. It means that I can effectively trust the compiler to generate both the to capture the pointer that I have created into the heap, and also to guarantee that it will be thrown away when I've finished with it. That's really, really powerful. But in order to be able to use that effectively, I need to be able to say, well, I've made one of these things, and I'd like to give it to somebody else now. But the uniqueness of unique pointer says that I can't have a copy of it. I'm not allowed to copy these things because it wouldn't be unique anymore. I'd either have to clone the object it's pointing at, which would be an expensive operation, or there would have to be two pointers pointing at the same object. And then I'd have to remember that only one of them is allowed to destroy it. It gets complicated. So the move semantics allowed me to wrap an object and say, hey, I'm giving this to you now, and my object is dead. And that's really powerful. We also got this thing called const_expr. Const_expr allows us to write compile time run code, or in principle, compile time run code. And this is a new laptop, and I haven't set it up for conferences yet. Means I've been talking about this for too long if the screensaver kicks in. So I can write compile time code, and if you've ever played around with like preprocessor tricks because you need like a constant that's available at compile time, then now you can write it without horrible macros. You can write it in the language you're already writing in. We'll see a little bit of that down the line, but it's a pretty powerful concept, and it's going to be built on in future. We've got atomics. Atomics let us access memory in a way that is multiple threads safe if you're careful. We get a memory model that allows threading to actually be well defined. We've got user-defined literals. There's tons of stuff. It was a huge reboot to the language. And then 3 years later, we got another revision of the language, giving us a whole bunch of stuff, including return type deduction. So now I don't even need to say what my function returns. I can just do auto myfunc, and then just do return 7. It's like, well, I guess you wanted this to return an integer, which obviously saves on typing, but in some generic code, that's a very valuable thing. Maybe I don't know what the result of what I'm going to return is because it's based on what I was given. So it's a powerful concept. And the Lambda support got even better. So now we can actually capture things and move them into the Lambdas. We can rename them. We can do some bits and pieces that allow me to more effectively use Lambdas. Lambdas became themselves constexpr as well, which is just another mind-bending thing. I can write generic code using Lambdas and know that they can be, in principle, executed at compile time, and the result just being fed out and might just be a number. So that's pretty powerful. And I have a friend of mine has done a presentation where he's written a compile time JSON parser, which is just nuts. Anyway, unimportant, using Lambdas. C++ 17, this is the most recent version of the standard. We got if constexpr, which is essentially an if statement that's run by the compiler with a constant expression, something which can be evaluated at compile time. And it works a bit like the hash if you've done, like, again, preprocessor hacks before now. So I can have a piece of code that's generic and maybe take some kind of type T that I don't know about, say a template type T, and then I can actually have conditional bits of code that say, well, if T is an int, then I'm going to do this thing, and if T is a double, I can do this other thing. And the important thing is that the stuff that's in the if statement just needs to be parsable. It doesn't have to be semantically correct. So if the failing case, if the else clause that wasn't actually run by my if is not well formed for whatever type it is, maybe it's like, say if T is a pointer type, then dereference it. Now, of course, if T wasn't a pointer type, that wouldn't be valid code. The compiler is allowed to throw that away now. And it gives us a powerful way for writing template meta programming, sort of very high order functions, without resorting to some of the old techniques that you probably have seen along the way that give the voluminous error messages that I alluded to at the beginning. We also got a whole bunch of new things in the standard, some algebraic data types, optional, variant. There's an any type that can hold anything. String view is like a window into an existing area of memory that lets us like look at a sequence of bytes as a string without like copying it. And these things are very, very powerful. So we've got a lot of cool things that have come down the pipeline, is what I'm trying to say here. And in C++ 20, which is already in the pipeline, we're going to get concepts, hopefully. We're going to get some ranges, which allow us to do like almost like pipe-based programming. You heard in the keynote, like Unix pipes are a forgotten thing, and I disagree with that. I use Unix pipes all the time, and it would be even more awesome to be able to take a range of values, pipe them through something which doubles them, pipe them through something which sorts them out, pipe them through something else, and then get a range out at the end and say, well, this is like my lazy evaluation of things. So that's hopefully coming. Coroutines as well, which will make network programming more palatable, hopefully. And these things are already starting to appear in compilers, which is amazing. So I want to just give you a quick example of how code might look different. I don't know if that's vague. Is that readable enough? I don't know if I can do much about the font size, so I apologize in advance. And I'll go through this super quickly. I'm not going to try and explain because I've already ascertained that most of the room is not currently doing C++ development. But this is like an old way of iterating over an array. The main sort of aspect here is this horrific variable I had to define that says, this is the thing, this is the type of the thing that I'm iterating with. And that's just horrible. So the first thing we could do is just replace it with auto, which is lovely. So I don't have to remember what my silly type is or how many colons or less thans or greater thans I need. But even better, I don't need to iterate over this anymore. I can use the range for. So then it just becomes that. Much nicer. Of course, if you're a functional programmer type person, You might know that there is a built-in function to C++ called accumulate, which allows you to say, well, here's the beginning of something that you can iterate over. Here's the end of something that I want you to iterate over. Here's the starting value. Just add them all up or accumulate them all, in which case you could write something like this. So I mentioned earlier about lambdas allowing you to write stuff inline. This is the opposite of that. There's my function at the top there that's accumulating. And in this instance, because I'm doing a root mean square, sorry, I didn't say that earlier, I need to take the partial sum and add the square of the thing that's being added to it to kind of get my sum of the squares before I square root it. So, I mean, it's not too bad in this case, but if you've got a big sprawling code base, having like loads of functions everywhere is just, cognitively loading. So you can write this, which arguably isn't much better, all things considered. But at least I've got my begin and end, my 0, and then there is my lambda, this block in the middle, that just says, hey, I just need a function right here that does this, please. So things have got a little bit better there, I hope. So C++ has changed. C++ has evolved a lot. And some of the things like the smart pointers are sort of game changers. You no longer have to worry about use after free or like memory leaks and various things like that. If you can rely totally on smart pointers to manage the memory for you, then you're in a good place already. But why would you pick C++ when there are so many other good languages out there? I mean, in particular, like things like Rust are really good choices for this, and I'm very excited about Rust. And I think probably, maybe I'm speaking out of turn here, but I wonder if a lot of the acceleration in C++'s development has come from like the fact that there is now a genuine competitor to C++. So I'm going to talk a little bit about why I think those value types, the first thing that I said on my bullet list, are really, really important. So what is a value type? It's an object that's passed by value. I'm not going to take reference to this thing. It's like either just an integer or a pair of integers or something that's small, maybe 16, 32 bytes worth of data for which it is cheaper just to copy around by value rather than having something in memory somewhere that I keep referring back to. And if you come from like managed languages, like Java in particular, it's hard to think about anything that isn't a reference because every object that you've ever dealt with is a newed up object that lives on the heap somewhere that you're pointing to. But there's a sort of category of problems that come with reference-based programming, and that is you don't know who else has got a reference to that object, and it's very hard for you to reason about whether or not that object is going to change under your feet. So if you've got a function that takes a reference to an object, and maybe you have some kind of listener callback thing, and you're writing your code, and your function runs, you do some work, and then you say, oh, I emit my something interesting happened event, and I don't know, somebody subscribed to it, they've done something with it, and then I carry on with my code. For all you know, all your references have gone and changed to be something else. That the object pointed to them has been mutated in some way, and that makes it difficult to reason about. So passing by value gets rid of that. You've got your own copy of that. That's really cool. In C++, value types have no overhead at all. They are literally the 4 or 8 or 16 bytes that are in a register somewhere or on the stack somewhere, and that means that there is just no overhead. I'm passing an int around, but it's not an int. It's my type, and my type can have behavior, so I can define what it means to add two of my types together. It can have I can write streaming operators for it. I can sort of make it my own, knowing that really it's still just a 32-bit value that's going to be treated as an integer somewhere. And they're really useful for things like positions, error codes, prices, quantities, times, anything where it would be really, really, really bad if you got things mixed up. I mean, so I worked in finance for a very long time, and you never want to get your parameters the wrong way round to your function, which I'll show you in a second. And it's just, there's a lot more, what's the word? Oh gosh, I had a good word for this, and my brain's gone blank. Not enough coffee. You're modeling your domain by saying that this is a type of this, rather than just saying int something in your function signature. You say, no, it's a quantity, and it's like, oh, that's handy. I'm documenting. It's. And so that C++'s strong typing means that I will get an error if, for example, if I were to write a function called buy shares, and it takes a const char pointed to the symbol, and it takes a double for the price, and I'm going to stop right here and say, never, ever, ever use doubles for prices. This is purely here as slide code. I will be lynched if anyone ever sees this in production code. And an int quantity there. And then I want to call my function with buy shares. I want to buy 800 shares of Google for $975, right? And the compiler will let me do this. And in very many cases, it won't even give me a warning that something's gone on because, whoops, I got the parameters the wrong way round. 800 is a completely valid double precision number, and 975.0 can be pretty easily coerced into an integer. And Microsoft's compiler, I think, whinges that you're like narrowing here. With the warning level cranked up on Clang, you'll get some warnings here. But it's the kind of thing you could imagine yourself doing, right? And it's the kind of thing that could be very, very expensive to get the wrong way round. So what if instead I'd written it this way? I've used my little tiny types, my price, and my quantity, knowing that they're really still just a register value. So I'm not giving up any performance here. And then I try and do this still. So I want to buy 800 at 975, and now the compiler tells me that I've made a mistake. And that's great. And it's the message is not the best, right? I mean, I'm trying to spin this to be like C++ is awesome and all the error messages that you've seen in your past have all been fixed, but that's not quite true. But that's not terrible. It's telling me like the second argument here, I couldn't turn that quantity you gave me into a price. And like, whoops, that's an expensive mistake averted. And so this is what a value type might look like. It's written just like a regular class or a structure. I'm just going to highlight some other new things that are new to C++ in the implementation of a value type. This is a two-dimensional position using floating point values for the x and the y. And so the first thing I'm going to say is like I can initialize my x and y in my structure. And again, if you guys are not familiar with C++, this is like news to us. I know Java has had it since forever. And the initializer here is the default initializer. I've just used open and closed parens here, which will mean it will be initialized to 0. But I could have also just done float x equals 0 or float x equals 10 or whatever I wanted the default value to be. So that's pretty cool. I'm going to skip that and come back to it. This is the constructor that says, OK, if you do want to make a position with a preformed position with an x and a y that I already know, then you can construct one with an x and a y. And I'm just going to initialize the x with the x and the y with the y that I passed in. That's pretty cool. Now, as soon as I start defining my own constructors, C++ says, OK, I get it. You want to do the construction yourself. I won't allow anybody to make a position without using one of the constructors that you gave me. But I just went to all this attention, this care, to make sure that like it would be initialized to 0 by default, right? So I want to kind of get that behavior back. I want to say, no. The empty constructor, the one that doesn't take any arguments at all, that allows me to just go pos p, that's just default. Bring that bound back, bring it back, and it will be default initialized to x equals 0, y equals 0. And just as an example down here, this is like how I start adding behavior. I'm saying like this is how to add a position to me to give a new position. So for those not familiar with C++ sort of idioms, the const explorer at the beginning is one of the new C++ 11 features, which says, look, in principle, this could be done at compile time. And if I were to do anything in here that was not in principle compile time doable, if I were to allocate memory in here or to throw an exception on a path where it would actually be executed by the compiler, the compiler would bug out and say, no, I can't do this. I can't do this at compile time. So it's completely unnecessary in this case. I'm just sort of exposing it here. I'm returning a pos object. I'm the operator plus. This is what happens if I add. The other pos here is when it's being added to me, and you'll notice that I'm taking it by value. This is the point of these things being value types. I can guarantee that it'll fit in a register or two registers or whatever, and it'll just come to me and be quick. And I'm returning a new position using the constructor I've defined above, just by adding things together with it. And then the thing that I really want to draw your attention to as non-C++, and this thingy doesn't work and it won't be on the recording anyway, is the const at the end of that line there. So the const explorer pos, operator plus, pos other, const. That is, I think, fairly unique to C++, maybe Rust as well, maybe anyone who's language expert here. It means that the object that this method is being called on is itself constant for the duration of this method. I can't mutate the object here. It's a big hint to me as a programmer that I'm not allowed to change myself, and I'm telling also my callers that you can call my method and nothing interesting will happen to the object. It will still be the same object afterwards. And that's I think, a useful thing and something I miss from when I do any kind of Java side work or stuff like that, where I get a method and your get method, you could potentially poke around inside your object and change things. So I quite like that. That's a nice thing about C++. And then you would do all the other operators, and you'd have a nice value type. A quick example of the clear object lifetime that I talked about earlier. So I mentioned that when an object falls out of scope, its destructor is run. And almost all languages have some notion of when my object is dead, I'd like you to do something for me. Java has finalizers, and C# probably has something similar, right? I'm looking at the crowd in case anybody can correct me again, I said I'm not an expert in anything other than, well, not even C++, but whatever. So the problem with finalizers is that they are run when the garbage collector or whatever mechanism is used to track when an object is no longer needed realizes that that object is unreachable. And that's great, but may not be a good time for you. So for example here, I've made up a database query function here, and this is the worst code, it's slide code and all that kind of nonsense. But on this line here, I'm this mythical DB connection object that doesn't exist anywhere, it's just made up, but I'm constructing one, and I'm giving it a hard-coded name of the server to connect to, called server, and port 9000, or whatever those parameters mean, doesn't really matter. But you know that if you're talking to a database, somewhere behind the scenes, there's going to be probably a TCP connection, so a socket's been created, a connection has happened, probably some buffers have been allocated on your side, and probably on the database, now you're taking up resources on this remote database. There's a connection on the database side that's taking up some of its RAM and is like got its buffer and its allocations on that side. So that's an expensive, heavyweight thing to do. And obviously in a real code, you'd cache it in some way and do connection pooling and all sorts of whatever, but okay, slide code. And then I'm going to call query, and I'm going to return the query. So I'm going to delegate out to whatever this query is going to do. Presumably it runs the query on the database and gives me a string of the result, like the worst representation ever of a query, but whatever. And I'm just going to return it to my caller. And that's great. What about that database connection? What about all the resources associated with it? In a managed language, you would probably have to do something where you explicitly call something to say like close, con.close, or you would have like a with block or some of the other sort of, I'm only familiar with Python in this particular thing where you do with open of foo as x, and you indent the block, and then at the closing of the block, then some magic method is called on the object that you withed with. And that's great, but you have to remember to do it. And this means I can write code, database connection code like this, which there's just no way to leave a dangling reference unless, as soon as that con object is not available to anybody anymore, then that connection is closed. The resources on my side are cleaned up, and the resources on the remote side will be cleaned up as well. And of course, there's a whole bunch of things to do with error checking and exceptions and stuff, so obviously, but I get to make up crappy code like this, and you have to kind of like invent the other bits for me. Another example now, this is sort of showing the transfer of ownership that I was talking about earlier, is like this example here where I have a document, and the document has elements, and the elements are like some virtual base class. That is an abstract class, an interface class for people coming from C# Java worlds. The problem with those objects is that I don't know how big they are, because it's up to the caller. The caller can make any implementation that conforms to that interface, and they can make any object they like and give it to me as an LM. So I can't store LMs myself directly. So I can't just have an array of them, and I can't just have a vector of them. I need to have references to them on the heap. And again, as soon as you start having references to things on the heap, you have to be careful about whose responsibility it is to clean up those references, those objects. So here what I've done is I've stored I'm going to store my LMs, if my clicker works, in a vector, which is to say a growing array of unique pointers to LMs. So the unique pointer is going to be the guy who's going to look after the allocation and deallocation, or rather the deallocation in this case, of those LM objects. The problem is, though, those unique pointers can't be copied because, again, they're unique. So how do we get things into them in the first place? Because someone has one and they're going to give me their pointer, and then I have to kind of, I need to get it in somehow without copying it. And the way to do that is with this horrific double ampersand thing here. Now, I will say that that's not a very good syntax for anybody, but this double ampersand here is called an R-value reference. And what this basically is a reference to an object that someone else has either promised that they're not going to use again, or it's a temporary value, in which case, by construction, you know that that object is about to die anyway. That allows me to steal the contents of that object, and then basically nuke the object that it came from. Now, you don't see that in this code here, it's all in the standard library at this point, but I'm accepting it. It's me saying, when you call my method add, you are giving me that object. That unique pointer is now mine. And then, because now my function owns it, my add function owns it, when I give it to the emplaceBack method of the expanding array, there's object array there, I have to say, well, I'm done with it now, I'm finished with it. I have to move it into the caller argument for that, the first argument for that function. So that's just an example of how ownership is being tracked and transferred now in modern C++. Finally, I wouldn't be able to go away without saying something about performance, and I realize I'm starting to run out of time. But I made up something using my funny little POS class that I wrote earlier to just sort of see how well the compiler could do with it. And here I'm using like the most functional way I could think of to find the midpoint of a bunch of positions, which is to say accumulate them all and add them all up together and then divide them by the number of them. That finds like the average of all the points, which is, if I'm not mistaken, the middle point. And of course, I couldn't do a talk without having a click on this. So this is an interactive view of that, and you can't really see. Oh, you can see it okay. It's the same code, and just to sort of give you, I mean, no one's going to understand what this is doing here. We don't really do. But what I want to just point out is that huge block of vmovs things here, the compiler is able to take advantage of the fact that it knows the memory layout of that array of objects. I didn't do anything particularly special. You've seen all the code. It's up on the slides. But the compiler is smart enough to notice that you've got x, y, and then the next one is, x, y of the first point, and the second point in that array will be the next x, y, and so on. So we've got this contiguous stream of x, y in memory. And it turns out that the CPUs have instructions which will just hoover up swathes of numbers and be able to add them in parallel to each other using these vector instructions. So the fact that it's lined up like this means that the compiler can take advantage of the memory layout, it can take advantage of the architecture, and it can generate code that is pretty much as fast as you could imagine. And I think for other languages where those things are not guaranteed stored contiguous, it's very hard for optimizing JITs and things to take advantage of that. I know there are things coming down the line, I think, for Java in terms of layout, and now we're into but wait, there's more of my sales pitch, and I'm going to blast through these because I would like to have time to have some questions at the end. Compilers. There are many compilers to choose from. Clang is now like probably the best one to go to. Nowadays, it is just awesomely well developed. It has amazing error messages, and it supports a whole bunch of tooling which allows you to interrogate and do like refactoring operations on your C++. Stuff like Google have really thrown their weight behind this as well. So Google are now sort of suggesting that if you're using any of their libraries, then you like just pick the latest version of the library and just continuously live at the head version of that. And every time they do a breaking API change, they're going to supply a tool based on like Clang, which will convert and move arguments around and do all sorts of clever things like that. So it's a kind of an interesting thing that the Clang, the compiler, has allowed us to do. GCC obviously is a classic, and both ICC, the Intel's compiler, and Microsoft's compilers are doing a very good job of tracking the most recent changes in the language. And GCC and Clang nightly builds will have almost all of the things that are even being just discussed on the mailing lists about what is coming in C++ 20. Sanitizers. So I've spun you this tale that it's totally impossible now to have any kind of memory errors in your program using smart pointers. Obviously, that's not quite true. There's always a way to muck this stuff up. But we have the sanitizers now. So if any of you have ever used Valgrind or heard of Valgrind, the sanitizers are like a version of Valgrind that compiles into your code. So the compilers themselves have flags that say, hey, generate bounce checks for everything. Hey, keep track of which things are live and which things are dead. Make sure that I can generate an error message at runtime, and it slows your program down, but at runtime saying, hey, you did something that was bad. And the problem, of course, and there are various types of sanitizers. We've got memory accesses, undefined behavior, thread safety. There's a whole bunch of things coming, but I'd just like to show you an example of what would happen here. So like, here's my dreadful piece of code, which is slightly surprising. The compiler actually compiles without any warnings whatsoever. But I have an array of 10, and I read the 11th element, which is, I think, actually 2 off the end of it. Now, if you were to look at the assembly code generated, well, forgetting the fact that it'll optimize the whole damn thing away, probably. If you were to look at the assembly, it would read off of the end of that array on the stack, and that's probably not going to cause it to crash. So it's like it's broken, but it probably won't even crash. But what you have got is, if you've got this kind of error, is a gaping security hole in your program where you're allowing somebody to read memory that they weren't supposed to be able to read. With the sanitizers on, and forgive the like shortness of this all, but the thing like 3 from the bottom here, with the big green line here, I get this error at the point that it happens. The program stops and it goes, whoa there, cowboy. You've gone off the end of the array here. You're poking around in the stack somewhere where you shouldn't be. You've probably got an error. And that's just awesome. There's even more output from that down below that tells you all the sort of other bits and pieces that are going on in your program at that time. And so if you've got like decent test cases in your code, and you should have, and you are prepared to build the debug and run all of your tests with the sanitizer on, then you're going to get a very good indication if you've done anything you ought not to have done, even by accident. And for what it's worth, like, although it slows your program down, I was able to run a fairly full trading system in debug with this sanitization on and still be able to like run it and not like time out. So it's fast enough on today's stupidly fast computers. Editors have gotten better. There are plugins for everything. You know, your VI, if you're a VI user, can have like autocomplete. The Clang tooling is available and it allows like a language server for C++, which is awesome. C-Line is just tremendous. If you used IntelliJ or any of the JetBrains products, you now have IntelliJ for C++, which is brilliant. The community around C++ in the last sort of 3 or 4 years, I think, has really, really picked up. Some of the members of the standards committee are putting out like core guidelines, clearly stating like, okay, well, we need to support these old things, but you shouldn't be using them anymore. You should be using these idioms and these ideas. And there's a library that goes alongside that allows you to better adhere to the recommendations that they've given. There is a very inclusive C++ community that has a bunch of it has a, what is it called, Discord channel. There's a Slack channel. There's some best practices. There's a lot of information out there. There are tons of things on YouTube if you're interested in like bite-sized best practices or like 5-minute videos about like, hey, here's a new feature of C++ you didn't know. It's really picked up recently. And so what are you waiting for? You should be giving C++ a go right now. Thank you, everyone.
So we've got 10 minutes for questions, I think.
Yeah, I think that's about right.
10 minutes. We've got one question in the app, but if anybody's got a question now, don't be shy. Go ahead and ask it. Otherwise, we'll read the one from the app.
There's one at the back there, yes.
Okay.
Hi. So the question was, if I'm a little bit aware of Rust, what do I see? I'm aware of Rust, yeah. I mean, I've written like 2 toy programs in it, and I've looked at from my point of view, I love performance and things, so I like wrote a ray tracer, and I was like comparing it with my C++ ray tracer, and I'm like, yeah, that seems pretty good, actually. So Rust brings almost all of the things that C++ brings, in total honesty to you. It is slightly, it's much, much stricter about the borrowing, which I've said is like moving ownership around. It's much stricter on that front, which allows you to be in a situation where if your code compiles, you probably aren't going to fall afoul of anything. You don't need a sanitizer as such in Rust because if the compiler compiled it, you're probably okay. Whereas with C++, it's still possible to play fast and loose, which is sort of part of the appeal because sometimes you know your own access patterns and it's very hard to prove to a static checker that the path that it's found by construction of your program can't actually happen. So I'm very excited for Rust. I don't know enough about it to comment more than that, though, but I think it brings most of the things that C++ has. Any other questions in the room? I was one at the front here. Hi.
So sanitizers you build with during development, but then you do not include them during tests and production builds?
So the question was, do we use sanitizers in debug builds but not in our production stuff? Broadly, yes. Although I know that Google are using some of the sanitizers in some of their core components just for security sort of checking reasons. So like cut down things for overflows of like signed and unsigned integers and some of the weird things the compiler can do around those. I think they build those into like core components of the Android operating system just to get the protection from it. They're like, performance is not as important as not crashing and not having a giant security hole.
So we got one question via the app, which I'll read to you. My biggest issue with getting started is understanding the ecosystem. How do you start a new project and add dependencies? What about deployments and build systems?
That is, yes. That is conspicuous by its absence in this talk, I'm afraid. The story is not good yet for C++. The best thing in terms of sort of getting yourself up and started with a hello world, I would suggest grabbing C-Line Community Edition and just saying file new project and sort of playing around with that. That's quite a good way of getting started. It builds a CMake project in the background and stuff. There's a lot of layers of things that are going on there. I'm not a fan of that myself, but it certainly gets you up and running quickly. In terms of adding dependencies, there is a couple of current like best of breed package management systems for C++. There's something called Conan. I haven't used it myself extensively, but it worked well enough to like follow the tutorial. But yeah, the committee are well aware that this is a problem now. And in fact, as of the last meeting, they have put together a new working group to try and make that onboarding process effective, the tooling around C++ much, much better, because it's compared to Rust. I mean, that's where Rust shines, right? I mean, this is a brand new laptop, and I needed to put a whole bunch of things on it, and I put Rust in, and I just clicked on the link and piped it through my shell, and I had Rust running, and then I just ran one of my projects, and it downloaded all the dependencies, and it built them all, and then it ran my application. I'm like, this is how it should be for C++, but it's not there yet. Yeah, I'm sorry, that's not the answer that the questioner wanted, I'm certain, but...
What would be a compelling reason to start a new project in C++? I find myself wondering. I mean, we just had a big appeal about fighting against entropy. Throw away the old code, start with new things.
That is very true. So yeah, the entropy that you mentioned too from the keynote, I think that is a real problem, but one man's entropy is another person's core component. And there are still some code in systems that I've worked on that have come from 10 years prior to my arrival, and those are probably written in C or early C++. And sometimes it's nice to pick that code up and just plump it in, and there's no interoperability problems. It's just a function like any other function. So there's certain things to be said for that. That said, the Rust story is pretty good, and its interoperability is I believe pretty good too.
Yeah, that's my biggest gripe with C++. All the old ways of shooting yourself in the foot are still there.
Are still valid. Yeah, I think I think auto pointer has actually been taken out now, which was the first aborted attempt at doing these smart pointers, and it just didn't work, and there were some horrific problems with it. So, but
any more questions from the audience?
Is there a TDD or BDD framework that you recommend?
TDD, I would recommend. I use Catch 2, I think it's called, and I think it has a BDD and a TDD mode of doing it. It's a header-only library. It's pretty straightforward to use. Okay. Oh, one there. Hi.
So I haven't done C++ since college, but my impression is that the standard library is rife with things that you should avoid. And I know there's Boost. Are there good places to go for a good, solid standard library?
So the guidelines support, the guidelines, whatever they were, I'll go back a couple of slides. Where are we? The core guidelines, which these slides will have links to them. They are pretty good about saying this part, don't touch that anymore. But they're a huge document. Now, I would say that the vast majority of the standard library is actually fine. There's no problems with it. I mean, things like auto pointer, which is like the one glaring problem, that has actually been removed, or it has a deprecation warning or whatever. I think you're pretty okay with that. Boost is a high quality piece of software as well. What else is there? No, I think it's probably Boost is the best one to recommend in terms of general purpose, like here are some algorithms. And I mean, that's another thing that C++ is a little bit weak on. You want to say, hey, I just want to change the case of my string. I've got my string and I want to uppercase it. You're like, here's this snippet of code that does it with a std transform of this to std to upper. And you're like, no, I want string to uppercase, please. That's what I'm used to in every other reasonable language ever. But these things will be coming down the pipeline. I think people are starting to realize that is a real barrier to adoption for people, is that if you can't just dive in and do the stuff you want to do straight away, then you're going to very quickly go, I'll go and do it in something else.
Any more questions?
All right.
In which case, thank you very much, Matt,
Thank
for
you
a
all
very
very much.
informative talk.
Thank you. Come and grab. There are some Compiler Explorer stickers up here if you want to come and grab one.